I've got to tell you, see what's in the ground before you dig it up. Needed a healthy hobby. She's proud of the call for your free venture. Part good stuff, treasure hunting.
All right, so that's one of the things that we will get to investigate. Let's talk about induction. All right, guys, take all the time you need to study this carefully. Believe it or not, we actually discussed this topic under a different heading. We discussed this topic whenever we were dealing with something that Tesla came up with, which is a transformer, right? Okay, so you got a primary coil, you got a secondary coil. You're trying to induce current in the secondary coil by using an alternating current within the primary coil. So how does that work? So that's what we will discuss. We're going to try to induce current in the secondary coil with something called mutual induction. All right, so the best thing to do is just move on to the handout. So just go to chapter 32. The inductance is what we're focusing on. Okay. So simple concept is this. Okay, so current here is current is moving in the downward direction just like that. So the current is gonna cause a circulating magnetic field. So the magnetic field does this because of the current. So it's just going into that region. Okay, notice that you got an AC generator, which means that the current here is gonna cause a change in magnetic field. So whatever this magnetic field is within this region, this magnetic field is going to be changing. All right, this doesn't have a good resolution. Let's do this. All right, so the intercepted magnetic field within the secondary coil is going to keep changing as well. So the strength of the magnetic field intercepted by the second coil is going to keep changing, which means that the flux of the second coil is going to keep changing. So which means that it's going to induce a current in the opposite direction of this current. All right, so there's going to be an induced current here, except the induced current is going to move in the opposite direction of the current within the primary coil because of the Lenz's law. All right, so that's a long conceptual connection there. Okay, so how do we mathematically formulate this or model this? Okay, so what do we know? The flux within the secondary, okay, we're talking about the magnetic flux within the secondary, is going to be caused by the current within the primary. All right, so the current within the primary is going to be responsible for the flux within the secondary. All right, so the current within the primary is going to cause the flux within the secondary. All right, and you can figure, and then you can increase the effect or magnify the effect of that flux by increasing the number of turns in the secondary. All right, so current within the primary is going to cause the flux within the secondary. And by increasing the number of turns, obviously you can increase the effect of the flux. That's what it means. All right, so flux in the secondary is going to be proportional to current within the primary. Okay, so using the way the mathematicians usually do it, you got a proportionality constant, and you got a proportionality, so you can turn it into an equation by using a proportionality constant. So M becomes your proportionality constant, otherwise known as mutual inductance. Proper unit is going to be H. H stands for Henry. Henry is someone that we discussed before. This is a high school physics teacher, Rochester, New York, and this is the guy who is the discoverer of the electromagnet. So the mutual inductance is named after him in his honor. They used Henry as a unit. All right, so his name was used as a unit, more like it. All right, but what does it mean? Guys, the M, the mutual inductance, is a magnification factor in this case, a proportionality constant, the magnification factor. So this tells you how much the current is going to be responsible for the flux in the secondary. All right, it's tough to describe it using just this equation, but this equation is the one that we will get to use in terms of defining the meaning of this. Okay. So what happens if you vary the current within the primary? Vary the current within the primary simply means the following. Okay, the strength of the current keeps changing. Not only the direction of the current is changing, it goes one way, and then you reverse the direction of the current. Now the current goes the other way, and then you reverse the direction of the current. It goes the other way. Okay. If you describe it this way and that way, the only thing which is changing is the direction of current. In reality, it's not the direction of the current is not the only thing which is changing. The strength of the current is also changing. It becomes maximized, and then changes direction, it becomes minimized, and then changes direction, it becomes maximized, minimized, changes direction, and then, all right, so the value of the currents is also changing. All right, because the value of the current is changing, which means that the strength of the magnetic field generated by that current is going to change, which means that the flux within the secondary is changing. All right, so when you change the value of the current, strength of the current, I don't know if the strength is the good term. When you change the value of the current within the primary, you change the flux within the secondary. And changing flux in the secondary causes an electromotive force in the secondary. That's it. All right, so any variation of the current within the primary cause a variation of the flux within the secondary, which is responsible for the electromotive force in the secondary. And the electromotive force in the secondary is obviously is going to drive the current in the secondary. So that's what we end up getting. All right, so now we have a better understanding of the mutual inductance. So the mutual inductance is going to tell you how much the variation of current in the primary is going to cause an electromotive force in the secondary. So how much the variation of the current in the primary, to what degree the variation of the change in the primary is going to cause an electromotive force in the secondary. Okay, so that would be a better definition of it. All right, so when you vary the current within the primary, it's going to induce a voltage on the secondary, and the voltage in the secondary is going to drive the current in the secondary. Okay. So this is known as mutual inductance.
The most common and thorough technique is the minesweeper. It's also the most dangerous, putting a man right in the heart of a live minefield. It's really just a supercharged metal detector, like the kind first used in World War II. The only real difference is that today's mine detector is lighter and much more sensitive.
Right now I'm clearing a path approximately 1 meter wide. This path should be wide enough to accommodate a platoon of Marines.
Slowly, the sweeper moves forward until...
What I'm doing right here is I'm finding the boundary of my signal. I picked something up in the deck. I'm just marking it so that my prober can come up.
What do you got?
I've got my left lateral limit. There's a scratch in the deck here. You see it?
Yes.
Using a probe, the combat engineer delicately explores for any hard contact. When he finds something, the soil is brushed away.
You've got some green plastic down here.
When the mine's uncovered, a TNT charge is placed.
Oh, smoke.
And detonated.
All right, so how does the metal detectors work? Here's a simple design. Okay, how would you analyze this design if this were a test question? Can you see what's going on in terms of the design? So let's just focus on this one. So this is the receiving coil, and this is the transmitting coil, right? So this is the current in the receiving coil, and the current in the transmitting coil. All right. Do you notice that the current keeps changing direction? All right. So which means that the
No, I didn't notice.
Okay, no, that's fine. You make the assumption that that's okay. So now that we notice it, okay, ignore the receiving coil. Let's take a look at the transmitting coil. So which means that the current keeps changing direction, right? So which means that the strength of the magnetic field is going to keep changing, correct? All right. So let's focus on the buried gold coins or metal in general. So Ian, explain what happens to the metal buried in the ground, or what's going to happen to the metal in general.
It would potentially be magnetized.
Or okay, so okay, let's get back to this one. I'm going to give you 5 points for saying the wrong thing. In this case, gold cannot become magnetized. Aluminum is not going to get magnetized. Gold is not going to get magnetized. So what happens if you vary the strength of the electric field within this gold?
Will it generate a current in the gold?
Yeah, it's going to generate eddy currents, right? So it's going to generate these circulating currents. So if there is a circulating current inside the metal, what happens? It's going to generate its own magnetic field, right? So it's going to, if you vary the strength of the magnetic field within this region, it's going to cause eddy current. So this current is going to go this way. If you diminish the value of the magnetic field, the current is going to go the other way. It's going to go this way and that way. So that in turn is going to generate its own magnetic field lines going this way and that way. Okay, I want you to notice that this receiving coil is oriented 90 degrees to the transmitting coil. The reason is because none of the magnetic field lines generated by the transmitting coil could be intercepted by the area of the receiving coil. So it's not going to cause any change in flux within the receiving coil. However, these buried gold or aluminum or what have you, when you start to generate these eddy currents, the eddy currents will generate their own magnetic field lines. These magnetic field lines will be intercepted by this area, right? So the strength of the magnetic field generated by these eddy currents within these pieces of metal will become intercepted by the area of the receiving coil. So if there's a change in flux, it's going to cause an alternating current here as well. All right, as soon as there's an alternating current there, obviously it's going to start to beat. All right, so that's the metal detectors work on induction, mutual induction. All right, so we discussed mutual induction. We worked on the mathematics of it. And there's also something called self-induction. Okay, so self-induction is an interesting concept. This is an important concept. And let's try to figure this out. Okay, so you got the current. and you keep changing, varying the value of the current, right? Okay, the current generates magnetism. And notice that that magnetic field also is going through the loop. This is a coil that you're looking at. This is like a solenoid in this case. So the strength of the magnetic field intercepted by the coil is going to keep changing. In turn, it's going to generate an electromotive force opposing the original current. So there's going to be an induced current, which is going to oppose the original current. So which means that it's going to put the brakes on. All right, so that's known as self-induction. So, okay, so self-induction is the same principle, same concept. All right, notice that the current here, okay, this current, and because the value of the current keeps varying, the current itself is going to generate a magnetic field. So the magnetic field lines do this. And the value of the magnetic field intercepted within that region is going to keep changing. So the current causes flux within this region, okay? And then you can magnify the effects of the flux by increasing the number of turns. So that's what we're dealing with. Once again, the proportionality, using a proportionality constant, can be turned into an equation. All right, so this becomes self-induction. So if you vary the value of the current, and that's what it says, so the time variation of the current is going to cause an electromotive force opposing the change in flux. All right, so now how much the variation of the current is going to cause an electromotive force is determined by this proportionality constant, known as induction. Okay, so that's the explanation for it. All right, so when you change the value of the current, it's going to cause an opposing electromotive force. Electromotive force is going to point in a direction that's going to oppose any change of flux. This derivation is going to be important. A lot of the derivations are kind of abstract. The ones that I'm interested in are the ones that you guys will need for problem solving purposes. Okay, so this is one of those derivations you will need in the future as well. All right, so how do you figure out inductance? Okay, so we know that it's a proportionality constant. It's going to tell you how much the change in currents is going to magnify the effects of the electromotive force. All right, so you start off with the basic equation of inductance. So isolate L, and so you're right over here. All right, so next thing is the flux is a combination of strength of the magnetic field being intercepted by the area. And for you to be able to solve this problem, you need to focus on the geometry in this case. Guys, when you have a coil like this, all right, this is actually a solenoid. All right, so the strength of the magnetic field inside a solenoid is given by this formula right here. All right, so that's your solenoid. All right, so you substitute here, and then this expression is going to get substituted there. So you do a back substitution, and all of a sudden you come up with this expression. Obviously, the current values will cancel, and then this is where you are. Okay, now let's focus on this one. Inductance is going to depend on the cross-sectional area. All right, so obviously you got your constant, so this is just a constant, so we can ignore that. Also, it depends on capital N and the lowercase n. All right, so this capital N represents the number of turns that you have. All right, so 1, 2, 3, 4, 5. So that's the number of turns that you have. All right, and then you have this lowercase n. All right, so this lowercase n is your turn density. All right, so this is 1, 2, 3, 4, 5. These are the number of turns that you have within the length of a solenoid. So divide the number of turns per length is going to become your number of turns. This is your turn density, number of turns per unit length. All right, so in essence, this term and this term are related using this equation. So this is number of turns per unit length that you're looking at. So this is substituted back in here, or this is being expressed in terms of that is going to give you this expression. All right, so you can, depending upon the test question, just know how to use this term and then relate these two to each other. Okay, so what do we know? Here's what we know. Inductance is going to depend on geometry. It's going to depend on the cross-sectional area, and it's going to depend on the number of turns per unit length. This is your cross-sectional area that you're looking at. So inductance is going to depend on the area. It's going to depend on your number of turns. All right, so it's going to be your number of turns. And it's going to depend on the length. And that's it. So it depends on the geometry in essence. All right.